So hello everyone. It's been a long time I upload any analog question, analog video on my channel. So from now on, I will focus on my analog questions. So I will try to be consistent to upload at least one question and or one interview question for you guys. So our today's question is why BJT Cascode has limited output impedance, which is beta or not. Like I record this question before, but somehow didn't click on the mic button, so I didn't record any voiceover. So I saw every question and then I realized that I didn't on my mic. So I will explain from here. So no need to write again. Uh, so if you have any doubts, then uh, ask in the comment section. So let's move to analysis. Like, what is the purpose of this analysis? Like, it can be a potential interview question. Like, it is not asked in any interview, but I think it can be a potential question. That's why I am doing this analysis. So, in our BJT cascode, there is the output impedance of the BJT cascode is limited by beta R naught. And why is that? Like let's move to the analysis. Like for this analysis, we have to understand the cascode T model. Like this is our T model. Like we have to understand first the T what is how T model looks. So this is our T model. So first learn about T model, then uh, come back to this analysis. And then what is the meaning of the cascode? Cascode meaning is cascaded cathode. So C is cathode, so it is cascaded cathode. So this is the meaning of cascode. First learn about T model, then come back to the solution for this analysis. So I am taking one common emitter stage with the emitter degeneration and with the current with constant current biasing. And let's move to this. Let's move to T model. First of all, why we use T model? Like there is two model. One is T model, and another is small signal model. And there is no full-fledged confirmed rule to use T model and to use small signal model. But there is some analogy. Like if you have any resistance in emitter, like emitter degeneration, then use T model as this make our analysis much more easier as compared to small signal model. When to use small signal model? When emitter is connected to ground, and when to use T model when emitter is connected to some fixed potential or some resistance. Then use T model. Like in this case, emitter is connected to RE, and we can assume this node potential is V. So it has some fixed potential VE. Okay, so we are using T model as emitter is connected to some resistance. So it is not a perfect rule, but yeah, we can follow this. It will make our analysis much more easier. So for this is our T model. This is our dependent current source alpha A, and alpha is a transistor parameter, which is usually one, as it is the ratio of current IC over IE. It is always less than one. So less it is not equal to 1, it is always uh, much closer to 1 and always less than 1. Okay, so this is our dependent current source LY, and T model is like a small signal analysis. So the constant sources are off. So this is our constant source, which is ground, and this is our constant source I naught, which is open circuited. So we have to find out output impedance of this stage. So this is our alpha E. This is our and from alpha E to emitter, our current becomes IE, not alpha E. From collector to emitter, our current becomes IE. And this is our alpha RM. This is our output impedance R naught, and this is our uh, connected resistance RE. So let's simplify this circuit. This is simplified version. Is this is our current source alpha A, this is R node, and this is RE, which is connected like this, and this is RM, which is connected like this. So I'm showing this here, and there is a one current flowing in RM, which is shown by this current alpha I as it is uh, going going to this node. Okay, so for to find output impedance in any circuit, we have to give a constant voltage source and measure the constant current, and the ratio of these two parameter will give output impedance. So Ix current is equals to I current is this, and alpha IE. So first of all, find the alpha A. Alpha A is like this. So if this is I current, it is we use current dividers and current divider analogy and find out the IE current, and IE is negative current as uh, this is going from ground to this node, so that's why I put negative, and which is RE alpha RM plus RA. This is simple current divider rule. It is not much uh, difficult. So this is I, and if we put I R naught is very large. R naught is much greater than parallel combination of alpha RM and RE, as alpha RM is much of 100 to 200 ohms, and RE is of around kilo ohms. So this resistance alpha RM is dominated by alpha RM is dominated in this branch, and alpha RM is much smaller. It is around 100 to 200 ohms, so it is much smaller than as compared to R naught. So the overall impedance of this branch is R naught. So mm, we will assume the overall impedance of this branch is R naught. So the voltage across this resistance is R naught, and uh, voltage across this resistance is Vx, and the resistance is R naught. So we can find out I. So I is Vx by R naught. So now we know what is I. So put in put in this equation and find the IE. Now from equation first is this I plus alpha A. So from this we can see Ix. Ix is equals to minus alpha Re. I just simply put the value which is Vx by R naught, and after solving, after simplified, we will reach to this equation which is Vx by R naught bracket Rm plus Re 1 minus alpha by alpha Rm plus Re plus alpha. Like you can solve by yourself and then come back to this equation, and this component is 1 upon beta. This expression is 1 upon beta, as beta is equals to alpha minus 1 upon alpha. So this is and if we simplified more, like then R out is Vx by Ix is equals to R naught Rm plus Re by alpha Rm plus Re by beta. So this is our final expression for this, and alpha is almost 1 and beta is from 100 to thousands. So in this we have three cases, like case 1, case 2, and case 3. We have to focus more on case 3, but now we will move step by step. For case 1, like we assume Re is much less than Rm, much less than Rm. So Rm is much greater than Re. So the expression reduced to this R naught Rm by Rm, which is cancelled out and becomes R naught. Okay, like it is looking like this simple BJT stage where emitter is connected to our ground. There is no any such resistance, as R is much smaller. So this is behaving like this. This stage has R output impedance of R naught. So we can see this expression as well. So R out is R naught for this case 1, and for case 2, Rm is greater than Rm, but Rm is less than Re, not much less than Re. These two are comparable, like Rm and Re comparable, but Re is greater than Rm, and but alpha beta Rm is much greater than Re, and beta Rm is our R pi. So if we put this in if we put this in expression, like Rm and Rm plus R is comparable, so I am writing both as it is, and alpha is 1, so I am neglecting alpha as well, and Rm is in this case uh, if we see here, R is much less than by much less than as compared to beta Rm. So Re by beta is also much less than Rm. So I'm rating Rm as it is, as Re by beta is much less than Rm. So if we solve this, this will become 1 and this will become Re plus Re by beta Re by Rm. So it will reduce to this expression like R out is R naught 1 plus Gm Re. Like in most cases we are we are in this case like where Re is greater than Rm but much less than beta Rm. So our out become 1 plus beta 1 plus Gm Re. But to uh, increase gain, this but to increase gain we have to increase some parameter which is like in this case which is if we see the state model which is alpha R which is Rm R naught and and this degeneration resistance Re. So this alpha Rm is set by our fabrication engineer, our design engineer, which designed this parameter and this R naught as well. So we can't increase uh, this much Rm and R naught, but we can change this Re. So we are focusing Re. If we increase Re gradually to higher values. So it will saturate our out. Like are you understanding my point? Like why we are focusing on RE as RM and R as RM or RM and R dot is fixed. Like it is fixed by the engineer, not by not by us. So we have only one option left to increase our output by adding more and more resistance in RE. But in the BJT case, if we add more and more resistance in RE, like if we increase our RE to higher values, it will it will saturate our output to beta or not. That's the point of our whole analysis. Why beta or not? As in case third, in case third, our RE is much greater than our beta RM. So our RE by beta is also much greater than RM. So what will happen? Like if Re by beta is much greater than Rm as beta is from 100 to 1000. So this Re by beta is this Re by beta is 100 times lesser than Re, and but it is much greater than Rm. So this will definitely much greater than Rm. So are you getting my point? Like this is a small quantity, this is large quantity, this is small quantity, this is also a large quantity, but is smaller than this Re by alpha is 1, but beta is 100 to 1000. So we will get to this conclusion like R out is Re by alpha, Re by beta, Re to Re is cancelled, Re to Re is cancelled. So R out R out becomes beta R naught. Okay, so this is our conclusion. Like why our R out saturates beta. We increase our Re gradually from 100 to 1000 to 100,000 to mega, sorry giga, then mega. So eventually, if we increase this to infinity, that then our R out that our out of this uh, common emitter with degeneration stage will become beta R naught. So this is our conclusion. But in most of the case, we are using this configuration as it is much more reliable. R out is R naught 1 plus B GM RE as if we stack much more BJT, then we will get output. We will get gain in GM R naught square condition. So this is also higher value, but sometimes we increase RE in that manner that it will try to saturate our output resistance beta R naught, output resistance to beta R naught. Okay, so this is my whole point. Like if we increase our RE to higher values, then it will try to saturate our output impedance in beta or not. Now we can see this in our cascode stage. Like this is our two-stage cascode, not two-stage. Sorry, uh, the two BJT cascode stack one by one. So this is Q1, this is Q2, and I think I can redraw this circuit. So I am using a constant current source for biasing I note. This is our VCC, and this is our V bias, and this is our V in. This is our transistor Q1, this is our transistor Q2, and this is V naught. Like if we see output resistance from here R out, which is R naught, and if we see from here, like this for this Q2 BG, for this Q2 transistor, this R naught is very large, and it is in emitter side, so this will become beta R naught, as this R naught is very large. So our R out of this stage will become beta R naught, and our gain will become minus GM beta R naught, as our GM is like our small signal current is GMV in, so our GM is GM1, so GM1 beta R naught. So this is our gain for this stage, and the output impedance of this stage is beta R naught. And if we see this in triple cascode, so if we see this in triple cascode, I note this is our B in AB bias, and this is our also B bias Q1, so Q2, Q3, Q2, Q1, and the small signal current is GMV in, and this is our V out. And if we see the output impedance on each transistor, so in for this transistor this is R naught, and for this transistor is beta R naught. So R naught is of 100 kilo ohms, and beta R naught is of beta is of 100 into 100 kilo ohm. So it is in mega ohms. So for this Q3 for this Q3 transistor for this Q3 transistor, our beat our emitter has resistance which is in mega ohms. So for this Q3, the output impedance, if we look output from this collector of Q3, then our output is beta R naught. So it is not beta square, it is only beta R naught, as it is saturated by this resistance which is beta R naught, as beta R naught is very large. So that's why the output impedance is saturated to beta R naught. So we can't increase our output impedance beyond this beta R naught. So that's why there is no point adding in multiple cascode stage in BJT, as this is only increase the input and output swings and increase the power supply, not suitable for our low powers devices. In it increase the headrooms, like headrooms is what headroom is like output and input and output swing. Okay, and it will consume much more power without any change in gains. Like the gain for this is like minus GM beta R naught. But if there is case of but there is a case of case second, like this case second. In the case second, what will the gain will become minus GM, and the output impedance of this will become 1 plus GM2 RO2 and RO1. So if we assume everything is same, like Q1 and Q2 transistor is same, then it will become this is GM1, and as and it will multiply to this and uh, go to a and become a larger value, which is gm2 ro2 ro1. So this is gm1 and gm2 ro2. So this is gain if we consider case second, but in case third the gain is limited, which is gm1 beta r0. So this was gain in case third, and for this the case third for this the gain in case third is also gm beta r0, but for in case second, like it will this will become uh, 1 plus gm2 ro2 ro1 like this, and then again it is degenerated by this stage. So eventually it will become much more large resistance. So you can try by yourself. So like this is my point. So the point is like if we in case third, the output resistance of any any cascode stage is limited to beta r naught. So that's why we can't see much. That's why we can't see triple cascode in BJT more frequently. We can see in a uh, most device, but not on BJT. So that's my video. And I want to conclude this video by this, like the gain is saturated to beta r naught, and this is my analysis. Like it can be asked by interview why uh, why the output resistance of BJT is saturated to beta r naught. So I think this is the solution. So thank you for watching. I will bring more videos on analog from now on. So thank you.